derived here and it will be simulated in MATLAB. So we will spend approximately 1 hour here, and when everything is clear I will tell you the parameters also, that take this L, this R, this is the switching frequency, everything. Then we will go to the that laboratory and we will try to simulate it and we will try to get it the results, desired results. Okay. At any moment of time if you are not getting, please raise your hand. I am here to help you. Okay. Because if I need to learn, I have done already. Okay. This is single phase half bridge. Okay. The terminology is like this. This midpoint is known as pole. So pole A, pole B, pole C in 3 phase. The midpoint is known as pole. Okay. And this point is taken as a reference, O. Switch S1 and S2, this is VDC. So what is the pole voltage? Two possibilities are there. When S1 is on, this is VDC. And 0 when S2 is on. And S1, S2 cannot be turned on at the same time because it will result into dead short circuit. Okay. So this is known as pole voltage. Now, I mean the average value which you need, this Vp, if you see, Vp is always going to be sit in between VDC and 0. Now you want some average value, suppose VDC by 5, VDC by 3, VDC by 2, 3 VDC by 4, something like that. So now you need to control this on time to get the required average value. Is it okay? Okay. Suppose this turn on time, this is S1, this is T on and this is T off. This total time is T. T on plus T off is equals to T, and there is one terminology, duty ratio. D is equals to T on by T. Okay. What is the average value of this pole voltage? How can you say VDC by 2? You are correct only, but very specific. So it will be VDC by 2. You are correct only. I am not saying you are wrong. Okay. So for when T is from 0 to T on, Vp is equal to VDC. When T is T on to T, Vp is equal to 0. what is the average value over a cycle? It will be 1 upon T, 0 to T, Vp dt. Okay. So from 0 to T on it's Vdc, and T on to T it's 0. Now I am writing each and every expression keeping in mind that secondary students are there. If MTech students are there, then I can skip this. I am writing each and every step. So this is VDC, it's constant, and this is T on. We have already defined this quantity, T on upon T. So average value of pole voltage is D VDC. So when I asked that what is the average value of pole voltage, you told that VDC by 2. It is correct, but for D is equal to 1 by 2. It can have any value depending on the D. D is a variable which can have any value between 0 to 1. So ultimately you can see that by controlling duty ratio, you can control the average value of the pole voltage, the output voltage, and you can have any value between 0 to VDC. So it's a controlled DC-DC converter, buck converter only, which is discussed in the morning, correct? If you think one step ahead also, you can modulate this D such that output voltage will be having a sinusoidal voltage also. Not getting, okay. No issue. I will try to. Though this is the next step, but just I want to give you the clarity. The shape of Vp pole voltage is being decided by switching provided at the terminal of S1, okay, because S2 is just complementary of S1. This turn on and turn off, keeping this time constant, you can vary turn on in such a way that the average value of pole voltage will have sine wave. Get it or not? Not get it. Again, this is the this is T, this is T, because I am keeping T constant. Now I am changing the turn on time sinusoidally. Here turn on time is T on is very less, then it is increasing, then it is increasing, then increasing. It will be maximum here, then it will be down, 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 down. So if I am changing this duty ratio, duty function, something like this, you know that duty time can have value between 0 to 1. So if I choose D carefully, like so D will be having between 0 to 1, and you find out this VP average. This is what? So it will be having this average value will be VDC by 2 plus VDC by 2 sin omega t. So you can modulate this switching sequence such a way that you can get a sine wave. If you find the average of output pole voltage, you will get sine wave. But yes, VDC by 2 shifted. So this output voltage, average value of the output voltage having two components, AC component and DC component. By the way, this method of PWM generation is known as sine PWM. Why sine PWM? Because the turn on time of the switch is modulated sinusoidally. Small, then increasing, then increasing, then increasing, becoming high. Getting my point? Okay. So if VDC is there, what is the peak value you can get for AC? If VDC is fixed, what is the peak value of AC you can get? This only? VDC by 2. Bolo? VDC by 2 will be DC, and peak value can have VDC by 2. Okay. So suppose you have single phase this bridge and you want to generate 220 volt AC 50 hertz, then how much DC voltage you require? 240 volt. Let me listen my question. What do you want? 220 volt RMS 50 hertz. What will be the minimum value of VDC? For 40 DC will work? Actually, out of VDC, VDC by 2 is the peak value of the sine wave. I am asking about RMS value of 220 volt. So out of 220, what will the peak value? Multiply by root 2. So this will be actually 220, and then VDC is calculated. This is the minimum VDC you require to produce that AC signal. Actually, inverter you have seen in simulation that this much the DC link voltage, this much the AC. Then how DC link voltage is calculated? So using this formula only. This is for modulation index 1. You have used full. I mean the sine wave is touching to 1. Duty ratio is touching to 1. If you are limiting it 0.8, modulation ratio is 0.8 only, you require more DC to produce the same voltage. Okay. Okay, coming to back. Can't you model this as a DP SPDT? Both are same or not? When S1 is on, it is connected to VDC. When S2 is on, it is connected to ground. And same this pole. So it's like a SPDT switch. What is the voltage here? In switch. Suppose this is switching function is S. So here S VDC. If S is 1, then VDC. If S is 0, then 0. If current is here I, then what will be current here? When S is 0, then no current. When S is 1, then same. So this current is also SI. So can't you model this as this SPDT switch like controlled current and controlled voltage source? Where this value is SVDC and this current is SI. So this is the actual model of this single phase half bridge cell, how it is modeled. So it's a controlled voltage and controlled current, combination of both. Suppose 3-phase inverter is there, then three cells will be there. And I will use this model only for subsequent simulations. This is average model. This can be this will act as a average model also. It can act as a switch model also. Depends which signal you are providing. So remember, the structure will be same. If you are using S, it is switch model. If you are using average value of S, which is D, so this is switched model and this is average model. For 3-phase inverter, what will be the structures? And then you can at any load. So this is actually 3-phase inverter. In switched model and average model depends which quantity you are taking. Here S, I will put SA, SB, SC. So SA How it is different from the model presented by Professor Karimi in the morning? There is only one difference. Difference is he has taken midpoint as a reference. Here he has taken one more battery and the value is VDC by 2, midpoint as a reference. I have taken single battery and reference is down. This is the only difference. So in his model, DC component will not be seen because it is switching between plus VDC by 2 and minus VDC by 2. In my case, it is switching between 0 to VDC. So AC component will be there, but it will be DC shifting of VDC by 2. But the peak value of the voltage will be same. In his case, VDC by 2, in my case also VDC by 2. Okay. So it depends on the book how where they are taking the reference, whether it's a capacitor midpoint or this lag low point, low point. Okay, this is how we are going to model the H bridge. This is okay so far? Okay? Okay. Now objective is this is H bridge. Again I am drawing. I want to control this current according to my requirement. I am saying control it at 500 ampere, then it should be 500 ampere. If 1000 ampere, then it should be 1000 ampere. What is the structure? The controlled model, it is shown in the morning. Input is D, then it will be multiplied by VDC. So here it will be dVDC, then minus Vs this is what current is. So by controlling D you can control I. This is the control model shown in the morning lecture. Now you want to control I. So what you will do? I reference, then this actual I, you will put one compensator and this will be giving duty ratio. Sorry, what किसी ने feed forward बोला है? Okay, मुझे लगा. So this structure we are going to simulate. So we need to tune this compensator CS. The parameters I will give you. Parameters are VDC is equal to 1200. Vs is going to be 400 volt. L is going to be 640 microfarad and R is going to be 5 milliohm. And switching frequency is something hertz. sorry. मैं फेराड लिख दिया था. No, no, no. It was done. My mistake was there. I don't want to hide. But my professor is very alert. I know. I was expecting same from you guys, but he told me that Farad लिखा हुआ है. They're very humble. Okay. Switching frequency is 1620 hertz. You want this IREF will be 1000 ampere. Okay. I will give you everything here so that you will not ask me anything there, that this parameter is not given. Simulation runtime, make it run for 2 seconds and provide a step change of reference. Here reference is 0 and here 1000. This is IREF. How many of you have used simulation? Most of master systems obviously they will be using base library, Simscape, specialized power system. Okay. Huh? MATLAB you will open in the lab. Then you will go to Simulink. Then you will go to Simscape. In Simscape you will go to there you will get source है ना, and passive, power electronics, switch gear and also, and whatever you want. We want one DC supply, two DC supply, R, L and switch. Switch is actually in average model we will use IGBT. In switched model we will use IGBT. In average model we will use controlled voltage source and current source. Okay. So it is there, controlled voltage source and current source is there in source section. Okay.
So you want them to use what? Switched model or average model?
Both. So here this is okay, you can start. When you will pick, when you will complete the simulation there, you will need one more block, power GUI. Okay, otherwise it will not, it will show error. Okay. Something more important, you will go to this simulation setting. Some symbol will be this. क्या नाम है इसका? Simulation setting? Model properties. Okay. So some setting symbol is there. You will click on that. You will find whether it will ask you whether it's continuous or discrete. That is in solver. Okay. So please choose no variable time and fixed. Variable time or fixed time. है ना? So use fixed. Choose fixed and choose TS to be sample time. Solver should be auto, no issue. We do not need a specific solver. And sampling time will be 1E minus 6. Click on power GUI. select discrete, put TS to be 1E minus 6. All settings are done. This is okay? Okay. In now I should tell you. Objective is same. We want to control the current 1000 ampere. Step change is there. Half bridge is there. I will model this average and switch as a. In average, it will be DI. स्टेप चेंज में लिखा है मैंने. Make it 1 second. Step change. Yes. And here it would be same but SI huh?
He's asking you to mention where is the current here.
Okay. I've already mentioned somewhere. Okay. You should have very good friends so that they can trigger you at any moment of time. Do this, do that. They will keep you updating and improvement will be done. Fortunately, I have such friends. If I have not mentioned current, they will let me know. And I am very thankful to my professor also. That sometimes my friend is not there, my professor is there, it's okay. He will manage all the things. So in system model we will be using S signal, and in average model we will be using D signal. Okay. The only difference is this IREF and I, when passing through PI controller, this will give you D. Okay. So that is to be utilized here directly, and when it will be passed through a carrier wave, then this switch S. So this becomes switched model, and if you are using only D, it becomes average model. What will be value of Kp and Ki in this case? I told you earlier in the previous class that if transfer function is 1 upon SL plus R, then take L upon tau, Kp L upon tau, and Ki R upon tau. Now the point is, what will be tau? I told you tau also, some 0.5 millisecond to 5 millisecond. Here I will give deep insight of that. See, when it comes to real implementation of power lateness converters, switching frequency is fixed. Like here, he has mentioned that 1.62 kilohertz. Okay. Why it is low? Because the numerical is dealing with 1000 ampere. If ampere is 100 ampere, 50 ampere, the switching frequency would be 10,000, 15,000. As you go for higher level, switching frequency goes down because of the switching losses in real applications. Okay. So how you will choose time constant? I am telling you, you first notice what is the switching frequency. The very first thing you need to notice, what is the switching frequency of your converter. Then convert it into omega s, which is 2 pi fs. And make one term omega bi. I will let you know what is this, and keep it this omega s by 10 to 20. Depends on your choice, whatever you want. Divide omega s by 10 to 20, 10 to 50, does not matter much. And then tau will be 1 upon omega bi. Actually, omega bi is the current controller bandwidth, which will decide the speed. Bandwidth. So this is bandwidth. So Kp will be L upon tau, Ki will be R upon tau. Now full parameters are given, you just need to simulate it. Everything is there. And see whether it is coming or not. When this is done, then I will tell you for slight modifications that okay, change this, change that, then observe. I will give you some problem will be there definitely, otherwise why you will ask. So if problem is there, then I will give you some solution also, that okay, now do this and see the result. It should improve. Okay. So far, if there is any issue, you can ask me. Especially BTech students, masters, I think they will be knowing. Bandwidth of the controller actually decide the speed of the controller. So the highest speed at which controller at this current can change, its switching frequency only. Suppose this is the switching triangular wave, carrier wave. You are changing modulation index here 3 times. How it is making difference? Ultimately decision will be taken here and here. In between you are changing 1000 times. It is not going to give effect on hardware side. So making current controller faster than the switching frequency is nonsense. Because it will not, it's something like that I am telling you up, down, you are able to follow my instructions. If I am telling you up, down, you cannot follow. Na? You have some limitations. So that limitation is switching frequency. Switching frequency, carrier wave is being compared with the modulating wave, then some pulses are being generated. Those pulses are deciding what current to be there. So if, and switching will happen here. So if you are comparing this, something like this, so it will compare this and this. In between you are changing anything. It will not reflect on the output side. So for effective decision, what is its maximum speed, that is switching frequency, make it 10 times, 20 times slower, current controller, so that whatever you say that okay, command is changed from this to this, so it can be picked by the control. Otherwise, if you will make this very equivalent W omega bi is equal to omega s, the control will not work properly. So so far I am talking about inner current control. Then after that some other control will come, outer voltage control. Then some another control, hierarchical control, anything. So the innermost controller is the fastest controller. As far as power electronics is concerned, the inner current control loop is the fastest loop, but it is less than 10. It is divided by 10, the bandwidth from the switching frequency. Then outer voltage loop, it will be slower 10 times at least than the current control loop. Then suppose PLL comes in the picture, then it will be slower than the outer voltage loop. So it's then only you can make the decision. Suppose we are in cascaded connected, I am here, here, something like that. So I need to pass the something. So I need to respect your speed also. If I am taking any decision very fast, it will not reflect in the output, and there will be mess up. It will be difficult to decide. Synchronous machine is not, why synchronous machine is not self-starting? Induction is there, synchronous is not self-starting. Why? Rotating manifold is also there. The point is you are asking someone to be Rajnikant. कि मैं बोलूँ टक हो गए. After 20 millisecond वो N से S, S से N हो जा रहा है. In 20 millisecond, rotor is having some definite inertia. It cannot reflect. That's why. Otherwise, you reduce the frequency. The same synchronous machine will start rotating. You will not need any additional damper winding and anything. That is a special type of starting method. Because now you have made that compatible कि आप तुम्हारे हद में है कि आप follow कर सकते हो उसको. This is how. So keep in mind, Professor Karimi will come with, he told in last lecture I will come somewhat, I will come to that level. If he is covering everything, it is going to be great. But I don't know, today he said that I will not be able to complete that. I wish I could complete 80%, 70%. I wish he could complete 100%. Then you will go through all three controller. Inner voltage control, outer voltage control, inner current control, outer voltage control, and then PLL. Everything will come in the picture. Then you will see that what should be the speed of this and that and this. And for BTech students, if you are not getting anything, so don't think that you are not understanding. If you are understanding, I will be surprised that why you are understanding. Because if I am saying that you got it, if you told me that, yeah, I got it, I will be surprised. Because it took me 10 years to understand all these things. How it is happening, why it is happening, actually what is happening inside. So it will be great if you get it, but I doubt. Okay, same thing we will try to do in the lab. How much time we have? No, it's done. Time is हो गया ना मैम उसका क्या स्नैक का okay. So any doubt is there what we are going to do, then I can entertain. सर कुछ भी आप लोग मास्टर्स PhD मास्टर्स ओके पावर इलेक्ट्रॉनिक्स पावर सिस्टम देन हम लोगों का अलग तरह रास्ता है. Okay, so please have a tea and we will meet in which lab? Which model is there, MATLAB? MATLAB 22A? 22A, okay. How many systems are there? 30, okay. So most people will get it. Okay? Okay, thank you guys. हाँ यार कनेक्टर तो चाहिए क्योंकि सर से कितनी बार लेंगे.